Hello, welcome to new session. In this session, we'll solve GATE 2016 executive many paper. Okay. First of all, one math question. In the parallel plate configuration shown, free flow of an incompressible Newtonian fluid is established by moving the top plate with a constant velocity u naught is equal to 1 meter per second. If the force required on the top plate With the force required on the top plate to support this motion is 0.5 Newton per unit area in meter square of the plate, then the viscosity of fluid between the plates is dash dash Newton second per meter square. Okay. So the force required is your 0.5 Newton per meter square. Okay. So that is the shear stress blunt according to Newtonian fluid. Okay. So using the Newtonian law, so we have tau is equal to mu du by dy, and here the velocity u naught. Okay, so u naught is your 1 meter per second. Okay, and this distance is your 10 or 10 by 1000. Okay, so du by dy is your 1000 by 10, and mu is your and tau is your zero point 0.5. So mu we can figure, so that will be 0.005 Newton second per meter. Okay. Next, for a newly designed vehicle by some students, volume of fuel consumed per unit distance traveled (QF in meter cube per meter) depends upon the viscosity mu, density rho of the fuel, and speed u, and size of the vehicle as QF is equal to C rho u square by rho u square L by del P. Okay, where C is the constant dimension of the constant CR. Okay, so putting the dimension of all the other parameters like QF is LQ by L. Okay, or L square, and rho is ML cube, ML minus cube, and U is your LT minus 2. Okay, and L is L, and dimension of viscosity as ML minus 1 to minus 1. So you have to remember this dimension. Putting these, you can get C. So C is your dimension of C are M square L minus T minus 1. So option B is the next. A semicircular gate of radius 1 meter is placed at the bottom of water reservoir as shown below. The hydrostatic force per unit width of the cylindrical gate in y direction in dash kilonewton. The gravitational acceleration g is equal to 9.8 meter per second square. Density of water is equal to 1000 kilogram per meter cube. Okay. So the force on the hydrostatic force per unit width on the cylindrical gate in y direction. Okay. In y direction means the vertical force is required. So force on this gate will be the weight supported by this area of this gate. Okay. For the curved portion. Okay. And the weight supported by the curved portion is your this is R. So in semicircle, so pi r square by 2 g into rho. So this is your vertical component. Okay. So this will be putting the value R is your 1 meter. Okay. And putting all the values, you can have 15.409 kilometer. Okay. Next, the velocity vector in meter per second for a 2D flow is given in Cartesian coordinate x y as v x square by 4 I minus x y j. The symbol bear usual meaning at a point in the flow field x and y components of acceleration vector are given as 1 meter per second square and minus 0.5 meter per second square respectively. The velocity magnitude at The point is dash meter per second. Okay. So your u is x square by u, and because this is your u, okay, x square by 4, and this is your v minus x square by 4. Okay. So ax is your dx du by dt, okay. So this is your okay, if you measure it, then it will be uh, sorry, expansion of this is curly by curly x by curly t, and curly by curly y, curly by curly t, curly by curly t. Okay. And u is not the function of t, so it is 0. Okay. And curly y by curly t, sorry, curly u is also not a function of y, so it is also 0. So we are left with this first part only. So it is curly by curly x is your 2x by 4, and u is your x by 4. So as the acceleration component in x direction is 1, so putting it equal to 1, so x is equal to ax cube is equal to a, x is equal to, okay. So ay, now finding out ay, dy by dt, curly by curly x by curly t plus curly by curly y plus curly by curly t. Okay, similarly that is that x direction curly by curly t. Okay, a similar manner. Okay, now v is not the function of y. Sorry, v is not the function of t. So curly v by curly t is 0. So it is curly y by curly t is your curly y by curly t is your, oh sorry, curly v by curly y. Curly y by curly t is your v, and curly v by curly y is minus x by 2. So this is your x square by 4 minus, this is your curly v by curly x, curly v by curly x is your minus x square. Okay, or oh, sorry, minus curly v by here it should be curly v by curly x. Then this minus 11. Okay. Okay. Now putting so cubic x by 4, curly x by curly t or u, so x by 4. Okay. So putting these values, okay, we have this, and ay as minus 0.5. So from this we can get y is equal to minus 1. Okay. Now we have to find out the velocity, velocity, the velocity moving at the point, at the point. So the point is your x is equal to 2, and y is equal to minus 1. Okay. So putting x is equal to 2, uh, where the acceleration is in x direction is 1 and in y direction is minus 0.5. The point is your x is equal to and y is equal to 1 minus 1. Okay. So u is equal to 2 square, u is equal to 2 square by 4, and v is equal to 2 by 2. Okay. So it is 1 and u is 1. So the velocity at this point is your u square plus v square 1 plus 1. V is equal to root 2. 1.414 meter per second. Okay. That is the answer. The optionless question. Answer is your answer 4 meter or root 2. Next, if phi xy is velocity potential and psi xy is stream function for a 2D steady incompressible and irrotational flow, which one of the following is incorrect? A. dy by dx phi constant is equal to minus dy by dx psi constant. B. Curly square psi by curly x square plus curly square psi by curly y square is equal to 0. C. dy by dx phi constant is equal to 1 by dy by dx psi constant. D. Curly square phi by curly x square curly square phi by curly y square is equal to 0. For steady flow, uh, the Laplace equation for this velocity transition should be satisfied. Okay. So this option is true. Okay. And for incompressible flow, the Laplace equation of the stream function should be given. Okay. So this option is answer true. Okay. So these two are true. Okay. And streamlines and potential lines are orthogonal to each other. So dy by dx phi is equal to constant. Dy by dx phi is equal to constant. Multiplied. Okay. Should be equal to minus 1. So the option C is and so the first condition is also subsidized. Okay. Because both lines are orthogonal to each other and their slope is the product of their slope is minus 1. Okay. U by d and minus is minus u by d. Okay. So it will be minus 1. Okay. So the incorrect condition is your this C. Okay. Option C is incorrect. Okay. What is the answer? The flow field shown for a bluff body has considerably curved streamline. A student measures pressure at point A, B, C, and D and denotes them PA, PB, PC, and PD respectively. State which one of the following statement is true. The arrow indicates the free stream flow direction. PA is equal to PB and PC is greater than PD. B. Option B. PA is greater than PD and PC is greater than PD. C. PA is equal to PB and PC is less than PD. D. PA is greater than PD and PC is less than PD. Okay. So at this point, at this time, when this body is rotating and flow is like this, then there exists a stabilization point. Okay, in between this region. Okay, so that is given by the amount of circulation given to the body or at a velocity of that. Okay, so this A point is your stagnation point. Okay, so the point so as it is stationary point. Okay, and the energy at A and B is same. Okay, so the pressure at the point A is the total pressure or stagnation pressure, and the pressure at the B is less than the stagnation pressure. So pressure at pressure PA will be more than P. Okay, and at C and D, velocity at C, velocity at sorry, at C, the velocity is there. Okay, so that velocity is your 2u. Okay, and at D, the velocity is less than the velocity at C. Okay, so the pressure at C will be less than pressure at D. Okay, because velocity because of same energy at C and D. Okay, so PD will be more than PC. So both conditions are satisfied in D option. Okay, D option. PA is equal to D. PC less than PC. Okay, so option D is right answer. Next, a 2D incompressible flow is defined by its velocity component in meter per second as u is equal to minus cy divided by x square plus y square and y and v is equal to cx divided by x square plus y square. If the value of constant c is equal to 0.1 meter square per second, the numerical value of vorticity at point x is equal to 1 and y is equal to 2 meter is dash per second. Okay. Now u is given that u is given the this and v is given the this. Okay. And to find out vorticity, we first of all we find out curly y and curly z. Okay. Now differentiating these, we have differentiation of this as c y square minus c x square, x square plus y square, y square. And similarly, differentiation of this we will have c square cy square minus cx square divided by x square plus y square, y square. Same thing. Okay. You can differentiate it. Okay. Using the formula for differentiation. So using divide rule. Okay. And we can have it. Okay. Now vorticity is nothing but the difference of these two. Okay. So as these are equal, so vorticity is zero. Okay. So answer is what? Zero. Vorticity is 2 into angular velocity or curly y minus curly x. Okay. So answer is zero. Next, two flow configurations are shown below for flow of incompressible viscous flow. The inlet velocity for diverging nozzle, figure 1, add free stream velocity for the flow past the bluff body, figure 2, is constant. The inlet velocity, okay, is constant. And the free stream velocity, okay. The point A and B are the separation point. So this is A and B. This is A. The flow is laminar. The relation regarding the velocity gradient at point A is Ty. In in the direction normal to the surface at the point of separation. Okay. So at the point of separation, curly u by curly y is 0. Okay. So as both A and B are the separation point, so curly u by curly y for both A and B should be 0. Okay. So it should be equal. So answer is what? A at the because the separation occurs at point where curly u by curly y and is 0. Okay. And for both are separating at A and B, so both should be equal. So curly u by curly y is 0. Okay. Next, consider a fully developed steady incompressible 2D viscous channel flow with a uniform suction and blowing velocity V naught as shown in the figure given below. The central line velocity of the channel is 10 meter per second along the x direction. If the velocity is the value of V naught at both the walls is 1 meter per second, the value of y component of velocity inside the flow field is dash meter per second. Okay. So here we can see that the air velocity and inlet velocity and our exit velocity are same. Okay. So it is not affected by the velocity in the direction. Okay. So the y component of velocity is there same. So at both walls and at the central end. So it is where V naught is there 10 meter per second. So that is the answer. Next question. 2 marks question. Exhaust from a kitchen goes into atmosphere through a tapered chimney as shown. The area cross section of the chimney at location 1 is twice that of that at location 2. The flow can be assumed to be inviscid with constant exhaust density at density of 1 kilogram per meter cube and acceleration due to gravity g is equal to 9.8 meter per second square. If the steady uniform exhaust velocity at location 1 is u is equal to 1 meter per second, the pressure drop across the chimney. So this is your chimney and 1 and 2. The one is having twice the area as that of 2. Okay, and at the difference is here 150 mm. Okay, so as using continuous equation, a1 v1 is equal to a2 v2. Okay, a1 by a2 is just 2. So v2 v1 by 2 v1 is equal to v2 and velocity at velocity at location is 1 meter per second. So we can find out velocity at location 2. Okay, Now we have velocity at location 1 and velocity at location 2 and head distance at 50 mm, 150 mm, kilometer head distance. Okay, so we can apply it further it is at 1 and 2, so it is there is no loss between 1 and 2. So applying Bernoulli equation. So V1 square by 2G plus V1 by 4G plus Z1 is equal to V2 square by 2G plus V2 by 2G plus VZ2. So Z2 minus Z1 is your on the speed, mm or 150,000 in meter. Okay. So V1 is your 1 and V2 is your 2. So it is 1 square and it is okay. And so we can find out P1 minus P2. Okay. So P1 minus P2 is your 2.7. The pressure drop is your 2.97. Okay. Next, a jet of diameter 20 mm and 6 meter per second coming out of water tank on a frictionless cart hits a wave and gets reflected at an angle with 45 degrees as shown in figure below. The density of water is 1000 kilogram per meter cube neglect the minor and viscous losses. If the cart remains stationary, then the magnitude of tension in the supporting string connected to the wall is. So this is your cart and this is the jet of water coming out at 6 meter per second at an angle 45 degrees. So here the diameter is your 20 mm. Okay, here the tension is here the strings. Okay, and here the diameter is 3 meters. Okay, and when this water comes out, the car remains stationary. Okay, and okay, when this water comes out, uh, a propulsive force will be acting on the car, which will try to bring it backward. Okay, but this string will hold uh, hold it. Okay, and so due to this propulsive force in that direction, okay, the tension in the string will be generated. Okay, so the tension in the string will be due to the propulsive force caused by horizontal component. Okay, as the car is at rest. Okay, so propulsive force is equal to tension. So propulsive force will try to pull it here and string will okay. Okay, and so the tension is equal to propulsive force. Okay, so that is mass flow rate to change in velocity in next direction. So here the velocity is your velocity of that jet is 6 meter per second or in x direction it is 6 force 45. Okay, so this 6 and initially it is at rest. Okay, so change in velocity is your 645. Okay, and mass flow rate is your 5 by 4 d square into 6 d is the diameter. Okay, and 6 is the velocity. Okay, so this is your tension. So 8 Newton is the potential in the string is 8 Newton. A block is floating at oil water interface as shown. The density of the oil in two-thirds of that water of the water. The density of the oil is two-thirds of that of water. We will come back after some time. Okay. हाँ जी